Hello everyone, I hope you guys are doing great. In this video, we're going to learn about the Axial connector in ABAQUS. This video is going to be related to this blog post from my website, Learn FEA. And please read this blog post before you watch this video, because this video is going to be more practical. We are going to open up ABAQUS and we are going to create a simple model using the Axial connector. Okay? So let's start it. Let's start by opening ABAQUS CAE. And let me already create a working folder for this project. Let me create a folder named Axial Connector. This is going to be our working folder where the files will be stored. Copy the path of this folder, and then here in ABAQUS, go to File, Set Work Directory, and then paste that path here, and then hit on OK. Okay, so everything that is going to be generated by this analysis is going to be stored in that folder. Now, to create the connector, we should go to Module Interaction. Now, as you can see in this blog post, to define a connector, we should define 2 points, points A and point B. These 2 points can be located in the same position or in different positions initially. But in 99% of the cases, the initial position is different for nodes A and B. So we are going to study this case. Okay, and by the way, guys, the axial connector is usually used to model axial springs, shock dampers, dash points, or node-to-node contact resembling a gap. I work with front suspension, the front suspension group of heavy vehicles, and I use axial connectors to model springs and shock dampers a lot. So this type of connector is very important. Okay, so let's define these 2 points here. To do that, we should go to Create Datum Point by entering coordinates. So click this option, and you see that here we can define the coordinates of this point. X, Y, and Z coordinates. The first point I wanted to be located in the origin of the global coordinate system. So just hit on enter, and then here we have the first point created. And now if we click on the plus button here in assembly, and here in features, you see that we have this point created. Now, the second point is going to be 50 millimeters upwards in the Y direction, as you can see here in this coordinate system. So I should define here the Y coordinate to be 50, and then hit enter. And we can see that point right now, and to be able to see it, click on out of fit view. And now we have the 2 points, this one and this one. Okay, so right now we have points A and B defined, which is the initial length of the axial connector. Now, next step is to actually create the axial connector. And to do that, we should use this tool, Connector Builder. Click on that tool, and then it says to select the first connector point, select this point, and then it says to select this second connector point. Click on this point. Okay, so our first point is the bottom one, and our second point is the upper one. Now this window appears, and this is the Connector Builder window, and you see that point 1 is a datum PT1, which is this first point that was created. And you see that there is a reference point that is automatically created at this point. That is RP1. And here we have point 2, that is datum PT2. And there is one reference point that is automatically created on that point too. And also, ABAQUS generates a wire feature automatically. And the next thing is to define a section for this axial connector, or actually for this connector, because right now ABAQUS doesn't know yet that this is an axial connector. But before we do that, let me just show you guys what we have here. So connection type, we don't have it defined yet because we should define this section firstly. And here we have CSYS1. So this is coordinate system of node 1. Node 1 was the first one selected, so it's this one, the bottom one. And when we create the connector, ABAQUS automatically creates a local coordinate system for this connector. And this local coordinate system is very important because for this type of connector, the axial connector, we can have only forces in the axial direction. And these forces are related to displacement in the axial direction, or even forces, actually velocities in the axial direction. So it is very important to have a local coordinate system defined because, as you can see here, we are going to select create coordinate system on axis between points. And then let's select 1. So that means that the software will create a coordinate system connecting these 2 points, where the axis 1, that is the x-axis, is going to be the axis that's going to be in the direction of this line connecting the 2 points. Okay, so in this axis, the local x-axis, we are going to have a possible degree of freedom, that is U1, and a possible force, that is F1. Okay, now coordinate system of node 2 is going to use the coordinate system of node 1. So in a nutshell, just one coordinate system will be generated, and this coordinate system will be positioned at node 1, and it's going to be used for node 1 and node 2. Okay, now we can create the connector section, and to do that we should click on create connector section here, and we can give it a name. I'm going to let the sender name, and then here we are going to tell the software what type of connector we want to model. So for axial connector, we should go to connection category basic. And you see that we can select here translational type and rotational type. For the axial connector, we have just translational properties. That is, we can only have forces related to displacements or velocities. And if we had like rotational type, we could have something like moments related to rotations, okay, which is not what we want. So here on translational type, select axial. Okay, now you see that available CORM is U1, that is the degree of freedom available. U1 is displacement in the x direction, local x direction, and we know that x is defined in the direction connecting the 2 points. Here we can click on show diagram, and then it shows this picture to kind of show how this connector works. So we have points A, points B. U1 is the degree of freedom that we have, that is displacement in the x direction. In this image, we see that we can have here spring forces, which is forces related to displacement. We have shock forces, that is forces related to velocity. Okay, click on dismiss, and Now click on continue. Now, in edit connector section, this window is very important because here we can define the behavior properties of this connector. Okay, so you see that we have behavior options, and here we have this plus button, add, and then we have some options here. We have many options, but the ones that are really used are elasticity, damping, and reference length. Okay, elasticity is when we want to define a relation between displacement and force. So imagine that, for example, we have an initial length equals 50 millimeters, and for this length we don't have any forces acting. And then imagine that we increase the length of this connector by 10 millimeters. Then we are going to have a final length equals 60 millimeters. Then we increased by 10, and then probably not. For sure, we are going to have some force related to that variation in length. Okay, just like how a spring works. And then we have damping. Damping is when we want to model a shock damper. For damping, we are going to relate velocity to forces. So it's just like a damping. When we have a higher velocity, we have a higher force, and so on. And reference length is the length where the axial force is equal to 0. It's like getting a spring unstressed with no forces acting on it. And then here there we have the length of the spring, that is the reference length. Okay, so these are the three properties that are important for us. And in this video, we're going to focus specifically in elasticity and reference length. Later, I'm going to create another blog post to talk about damping, because this one is important too. Okay, so let's define elasticity. And here we have some options. And here, for example, in definition, we can have linear, nonlinear, and rigid. The ones that are really used in practical applications are linear and non-linear. Let's start understanding how linear works. So basically, for linear, we can have only one stiffness that is constant for all displacements we can have. Non-linear, we can have a table defined where we have different forces for different displacements. Okay, we are going to see about non-linear later. Okay, let's start with linear. And then here we should select one of these options for force and moment. So for the axial connector, we can only have force in the x direction, local x direction, F1. So we can only have axial forces. We can't have any moments. This is a translational connector. And here we can define the stiffness for this connector. In my blog post, I explain really well how this stiffness works. So here we have one example. In this example, the initial length is 50 millimeters, and then the unstressed length, or the reference length, is 50 millimeters too. So initially, this connector will not have any forces acting on it. And then I defined a constant stiffness of 10 newtons per millimeter, which means that if initially we have 50 millimeters, and let's imagine that we increase the length by 5 millimeters, just like it's shown here, then we are going to have a force of 10, which is the stiffness of the connector, multiplied by the variation in length, that is 5. Then the force will be equal to 50 newtons. And since we are increasing the length of this connector, we are generating traction. which means that the external force should be like it's shown here, the red forces, and the connector internal forces will be one that tries to join the nodes back together. Okay. So this is how the stiffness works. And let's define it to be equal to 10 here. And in ABAQUS, we don't have units explicitly defined. So we should define the units that we want to work by ourselves. And these units should be consistent. And to define it, we should use this table, search for ABAQUS units table, go to images, and then we have this table. We should use one of these groups of units. So for example, let's use SIMM. So length in mm, force in Newton, and so on. Okay. So when I define here 10, I'm going to, this is 10 Newton per millimeter. Okay. Now, in table options, we have some important things here, but not for a linear behavior. When we get to talk about nonlinear behavior, we are going to understand what is here, what is it that is important here. Okay, now click on OK. And yep, now we are ready to go. Our connector is completely defined. Click on OK. And now we have our connector here represented. You see that we have our local coordinate system with the x-axis defined along the direction connecting the 2 points. We have RP1, RP2. This is an axial connector, and initial length is 50 millimeters. And I just remembered that I forgot to define the reference length. So let's go back here. You see that we have here connector section manager. Click on this. We have our section defined. Click on edit. And here we should define also the reference length. So click on plus reference length, and then length associated with U1, that is the axial direction. So for example, if we define the reference length equals 50, and we know that the initial length is 50 millimeters, it means that initially we will not have any forces acting on the connector. However, if we define the reference length equals 30 millimeters, and the initial length is 50 millimeters, then initially we will have the axial connector 20 millimeters with an increased length equals 20 millimeters. So it's already in traction. So we are going to have 200 newtons force, and that tries to join the nodes to get back together, the connector force, right? But the external force should be one that tries to pull the nodes apart. Okay, so for this example, let's define it to be equal to 50 millimeters and click on OK. So initially, we don't have any forces acting on the connector. Close this window. Now the next step is to define these steps. So as you can see here, we have already an initial step defined. And in this initial step, we can only define fixed boundary conditions to prevent rigid body motion. So let's fix one of these nodes. Let's fix the node A, that is this one, the bottom one. Click on this plus button. Click on BCs to define a new boundary condition. And then we are going to select this first option, continue. Deactivate create set. I don't want to create any set. Select this point, done, and select encastre. That means that we are going to fix all degrees of freedom of this node. Click on OK. And now on this upper node, I want to define a displacement in the global y direction, that is in the upward direction of 10 millimeters. However, to do that, I need to create a new step. And to create a new step, you can double click on steps. And then we have step 1 after the initial step, and it can be a static general. Continue. But here, one very important thing that we are going to do is to activate large displacements, because I want to do these analysis by parts. If I don't activate it, the solver will solve it at once, and I don't want that to happen. I want to have intermediate results. Okay. And here in increment size, I want to start with 0.1. The minimum should be 0.1 and the maximum should be 0.1. Okay. And let's remember that for a nonlinear analysis, this increment works like a percentage. So 0.1 means 10%. And that means that if I'm going to impose a displacement of 10 millimeters upwards, it's going to start with a displacement of 1 millimeter, and then after that, more 1 millimeter, and so on. And I define the maximum because if I don't do that, the software will just increase this increment. And initially, it's going to apply 10%. But after that, if it thinks it's an easy analysis to be converged, it's going to apply the rest of the displacement. But I don't want that to happen. Okay. All right. We don't need to do anything here. Click on OK. Now we have the step defined. It's right here. And here in BCs, we have BC1 that was created here in the initial step, and it was propagated. That's okay. I want to have this node fixed to prevent rigid body motion. And let's create another coordinate system. Double click on BCs. Select displacement. Continue. Select this node. Done. And I want to displace it in the global y direction. So you see that the coordinate system here defined is the global coordinate system. It's not that local coordinate system that was created here. It is the global coordinate system where we have the y direction being the upward direction. Okay, so for U2, that is the displacement in the y direction, I want it to be equal to 10 millimeters upwards, positive, and then click on OK. Okay, now I want to create another step to, after going up, I want to go down by 10 millimeters. So I want to compress this axial connector. Okay, so let's double click on step, and then it's going to create another step after step 1. Static general. Continue. Large displacement is activated. And then here again, 0.1, 0.1, and 0.1. Click on OK. Let's see. Here we have the two boundary conditions propagated. But this second boundary condition, I want to modify it. Instead of having positive 10 millimeters, I want to have negative 10 millimeters to compress the axial connector. Go to Module, Load, click on Boundary Condition Manager, and then you see that we have BC2. For step 2, I want to edit. So click on Edit, and then I want to have it equals to -10, and then click on OK. And you see that for step 2, BC2 is going to be modified. Now we can close it. And the last thing I want to define is the output request for this analysis. Okay, so let's define here for step 1, the field output request. Double click on this item. Let's deactivate everything. And let's go to displacement. I want translations and rotations. Okay. Now forces, I want reaction forces. Now I want also the connector outputs. But you see that we don't have anything related to connectors here. That's because to extract connector outputs, we should firstly create a set containing that connector. Okay, so click on OK, and let's create a set containing this connector. So here in assembly group, we have the set group, and then double click on it, and then let's name it as connector. Click on OK, select this connector, click on done, and then now we have this new set created. Now go to F output 1, and then select set, select the created set, and now you see that we have this item here for connector. We have some types of connector outputs, but the ones that are important for this type of connector are CTF, and which is total forces and moments, and CU, that is relative displacements and rotations. Okay, click on OK. All right. Now, this was defined for step 1. Now let's go to step 2, plus button here in field output request. And you see that the F output 1 was propagated. So what we have just defined here for step 1 is already defined for step 2. So we don't need to do anything. Okay. Now we just need to solve this module. To solve it, go to module job, create a new job. Let's name it as Axial connector linear. Click on continue. And then we can accept everything here. Click on OK. And go to job manager, and we can submit this analysis. And let's remember that we have set the working folder as this folder right here. And when we solve this module, now it's completed. The software creates these files right here. Okay. So for example, the STA file contains, let me open using Notepad, contains here's the steps and sub-steps information. This is the status file. The ODB contains the results. The INP file contains the module setup. So here we have the definition of the nodes. Here we have the definition of the element. It's a connector element in a 3-dimensional space that has just 2 nodes. The definition of the nodes, and definition of the steps. Everything that we have set up, we have it here. Output requests and everything. Okay. All right. Now let's post-process these results. Go to this job and then results. And we can't see any connector here. So firstly, we need to activate the visualization of the connector. And to do that, go to viewport and actually go to view and ODB display options, entity display, and activate show connectors. Apply, and there we have it. Now we can see the connector. Okay, now before we start post-processing, let's go to viewport and viewport annotation options, legend, and I don't want scientific format. I want fixed format. Apply, okay. Okay, now let's click on plot contours on deformed shape and go to CTF, that is connector forces, and I want CTF1, that is the force in the axial direction or X direction, local X direction, CTF1. And okay, you see that it's showing a local coordinate system here. It's weird because it was supposed to show the X direction in connecting the 2 points. So I don't know if it's some type of bug, but this is not right. Okay, it's showing Z, but it's not supposed to be Z. It's actually X. I don't know the reason for that, but it's not right. Let's even go to View, ODB Display Options, and then deactivate Show Local Access. Apply. Okay. All right. Now, let's go to Result, Step Frame. And then we have our 2 steps here. Let's start with Step 1, Initial Condition. So initially, we had an initial length of 50 millimeters. And you see that the CTF1 is equal to 0. So initially, we don't have any forces acting on the connector. Now, let's go to the first increment where we applied 10% of that prescribed displacement. So if we have 10%, we have 1 millimeter upwards. And you see that CTF1 is equal to 10, which makes sense because our stiffness is 10 Newton per millimeter. Now, if we go to 20%, we have 20 Newtons. And if we go to 1, we have 10 millimeters in variation in length, and therefore we have a 100 Newton force. And you see that this force is positive, and this is a convention here in ABAQUS for when we increase the length of an axial connector, we induce 2 tractive forces, and for tractive forces, we have this condition shown here. We would have the internal forces like the green ones, and the external force that we would have to apply should be like the red ones, should be like a tractive force. Okay, and here we have shown the connector force, and this is considered to be a positive force in this condition. Now for step 2, let's go to the beginning of the step 2. In the beginning of the step 2 is the end of step 1. So we have 10 millimeters positive displacement, and then it starts to decrease until it gets to, in the middle of step 2, it gets to the initial length, and then it starts to compress until it finishes with 10 millimeters downwards compression. And you see that we have a connector force CTF1 equals minus 100 Newton. Okay, so as a convention, when we decrease the connector length, if compared with the initial length or the reference length, we subject the connector to compression, and the connector force is negative. Okay, let me show one example. Yeah, it's this condition right here. So we have an initial or reference length, and then we decrease this reference length, and then we are subjecting this to compression. Then the internal force will be like the green one, and the external force should be like the red one, a compressive external force. Okay. And also we can check CU. CU is just the relative displacement. Let's start by step 1. So at first we have 0, and then at the end of step 1 we have it equal to 10. For step 2, initially we have it equal to 10. In the middle of it we have it equal to 0, and then here we have it equal to 10 again. So for this one we don't have any signs related to that. It's just a relative displacement with respect to the reference length. Okay, now that we understood how the linear axial connector works, let's understand how the nonlinear axial connector works. Okay, let's go to interaction again, and here in connector section manager, go to edit, and in elasticity. Oh, and just before we continue, let me show you guys one thing. Suppose that we define the reference length to be equal to 30 millimeters. Okay. Now go to job manager and submit this analysis again. Go to results. Go to result, step 1, initial step, and let's plot CTF1. Okay, so initially it's showing 0 force, but it's just because the analysis didn't start yet. So ABAQUS didn't read the initial conditions yet, that is the reference length. So let's go to this next increment, and you see that for this first increment we already have 210 newtons of force. That is because we have 1 millimeter upward, and we had already initially 20 millimeters, because the reference length is 30 millimeters, but the initial length of the connector is 50. So initially we already have 20 millimeters of variation in length. And then in increment 1, we have 21 millimeters, which yields to 210 Newton. Okay? So I think that now you understood better about how the reference length works. Let's go back to interaction. Connection section or connector section manager, edit, go back to reference length, and let's start it with, actually, let's define it as 50. And in elasticity, let's work with nonlinear. So here for nonlinear, we can define a table that relates force to displacement or moment to rotation. But here, since it's an axial connector, we can, this is force versus displacement. Okay, so here in my blog post, I have shown how this works. So basically, we define here a table that can be plotted like this. We can have a non-linear relation between force and displacement, just like it's shown here. In the vertical axis, we have force, and in the horizontal axis, we have displacement. So the relation between these two is not linear. This is very useful because this is what actually happens in reality. Okay. In many cases, we have this nonlinear behavior. In some specific cases, like for front suspension spring, we usually have a constant stiffness. But for example, in the front suspension of a vehicle, there is the jounce bumper, and for the jounce bumper, we have a nonlinear relationship between force and displacement. Okay, so let's define here a curve. And I have here a spreadsheet opened. Let me bring it. And here we have this table. Let's copy it. Let's see if it's gonna work. And let's paste it here. Okay, it worked. But I need to inverse this. So let me actually copy it here. And let me put it like this. Okay, force and displacement, Control C, and let me delete it, Control V. Right. Okay, you can define it manually in your case. In this blog post, we have the same table here defined. And let's understand how it works. But basically, you see that we have for 25 millimeters positive, we have a force of 200 Newton. For 15 millimeter displacement, we have a force of 150 Newton. Now for negative 15 millimeter displacement, we have a negative force too. So let's remember that for the connector force, a positive force means traction. That means that the final length of the connector is greater than the initial length. We are increasing the length of the connector by, for example, 25 millimeters. So in our case, since the initial length is 50 millimeters and the reference length is 50 also, if we displace this point 25 millimeters upward, then we are going to have a 200 Newton force, positive. And if we displace that node 25 millimeter downwards, we would have a force of minus 1000 Newton, and it's compressive. Okay, so you see that we can have different forces for equal displacements, for displacement for a traction displacement and compression displacement, the forces will be different. Okay. All right, so we have the table defined here, and let's click on OK. There is one thing that is important here to mention, but I'm going to talk about it shortly. Okay, let's click on OK, and then go to job, and let's create another job. And this one is going to be Axial connector nonlinear. Click on continue. Okay. Job manager, and then submit this one. And it's going to create some files here related to this analysis. Let's go to, so it's completed. Let's go to results. And then again, let's plot CTF1. Let's go to results, step frame. Let's start here. And then at the end of this step, we have 10 millimeters upwards. If we go to this table, for 10 millimeters, we would have 110 Newton force. Let's see if it's true. Yep, that's true. 110 Newton force, positive. Let's go to step 2, and then at the end of step 2, we have minus 10 millimeter displacement. For minus 10, we would have a force equals minus 200. And that's what we have. Okay. All right. Now let's do one last thing. We defined our table for a displacement from minus 25 to 25 positive. What happens if I cause a displacement higher than 25 millimeters? Let's see. Go to interaction. Actually, yeah, let's talk now about this new tab. So go to connector section manager, edit. In here, in table options, and you see that here we have some options for extrapolation. We have constant extrapolation and linear extrapolation. And in this blog post, I explain about it. So basically, if the extrapolation is constant, if we have a displacement higher than 25 millimeters, let's say 30 millimeters, then the force will be the force, the last force defined, that is 200 Newton. Okay, and if we have a displacement of minus 30 millimeters, we would have a force of minus 1000. It's something like this. We would have this force constant. Okay, this is what's going to happen. And if we define it as linear, the software will do a linear extrapolation, which means that it's going to get the last linear. So we have these. Let me get here. We have these two points here defined, and there is a line between these 2 points. There is this line right here, and the software will extrapolate using the inclination of this last line. Okay, so it's going to do a linear extrapolation, and I show the details of this type of calculation here. Okay, so let's define, for example, a linear extrapolation. Click on OK. Now go to step, let me find it here. Okay, step 1. Let's go to step 1. Actually, go to load and then go to boundary condition manager. And in step 1, we have BC2 created. Let's edit it. And instead of 10 millimeters, I want to have 30 millimeters. Click on OK. And here in step 2, instead of -10, I want to have -30. Click on OK. And let's go to job. And then let's submit this job again. Submit it. Okay. Now it's completed. Go to results and let's plot here CTF1 again. Let me zoom in. Go to result, step frame. Let's go to step 1. At the end of step 1, we have a force equals 220. Okay. And you see that for positive 25, we have a force equals 200. So for 30 millimeters, we don't have anything defined. But if you see here, for a variation in length equals 5 millimeters, that is 25 minus 20, we have a variation in force equals 200 minus 180, that is 20 newtons. So if I increase the displacement from 25 to 30, I should increase the force by 20 newtons. That is, I should have a force equals 220 Newton, which is what is shown here. Okay, so for step 2, let's go to the end of step 2. And then let's go back to this table. You see that here for -30, we varied the length by the displacement by 5 millimeters, which is the same variation that we had here in these last 2 points. So we should have a variation in force equal to what we had here, that is 400 Newton. So here I should have -1400, which is what I found here. Okay, so this is how the axial connector works. And this is a very important type of connector, guys. And there is one more feature that is important that I'm not going to show here, but it's related to damping. And for damping, we have a relation between force, axial force, and axial velocity. And to perform this type of study, we would have to perform, for example, an explicit dynamic analysis. Okay, but I'm not going to do this here in this video. I'm going to talk about this in probably in another blog post. Okay, so please read this blog post, and if you like content like this, content about finite element analysis theory or ABAQUS related stuff, you can subscribe to my FEA newsletter. Okay, you just need to insert your name and email address here. Okay, so thank you guys for watching, and see you in the next video.